and share screen because it takes a minute to set that up. Do this. Okay. All right. How's that look? Looks good. I noticed that some of the Zoom lectures from the math department are on YouTube. I was watching one on number theory last night, Math 115. It was kind of interesting. But somebody's done a little bit of editing of the videos. I don't think the ones I've put up would be suitable for that without a little bit of editing. All right. Anyway, in last lecture, we did some analysis of helium by perturbation theory. We analyzed perturbations of the ground state as well as the singly excited states. Those are the only ones that have any chance of not getting pushed into a continuum threshold when you turn on the perturbation. And basically what we got out of that was a qualitative description of the ordering of energy levels of the excited states and an explanation for some of the main features of the energy level diagram of helium. And in the case of the ground state, we got a much improved estimate, in fact, an upper bound to the true ground state energy. However, in the case of the H- ion, we failed to provide a theoretical proof that the H- exists as a bound state because we could not get a variational energy that was greater than the continuum threshold, which for H- is minus 0.5 atomic units. Okay, so that's kind of what we did in the last lecture. So tonight, the first order of business is to treat helium by the variational method. So let me show you how this works. A variational method involves trial wave functions, and you can choose any trial wave function you want. So there's many, many ways of doing this. We'll do it one particular way. So let me see here. Let me just get a single pad here. It'll probably work better if I do. Put that up here. All right, so to draw the picture, I've got the axes here like this, X, Y, and Z. And we've got the nucleus at the origin with charge plus ZE. We've got two electrons which are at locations out here in space somewhere. Let's call this R1 and this R2. And we'll call the distance between the two electrons R12. It's the same notation I used in the previous lecture. Now, in perturbation theory, we turned off the inter-electron interaction. And the result was the two electrons then are influenced only by the nucleus. So they basically obey hydrogen-like dynamics in a charge of +2. And speaking of the ground state of the unperturbed system then consists of two ground state hydrogen-like orbitals, which are sitting on top of each other. They're both of them are rotationally invariant, 1s waves, sitting on top of each other down there at the origin, near the origin. Now, when we turn on the perturbation, it's easy to see what's going to happen is that the electrons, these two electron clouds that are overlapping, the electrons repel each other. So the electron clouds are going to expand. It's going to be bigger than it was, move away from the origin. And at the same time, there's also going to be a tendency for the two electrons to be correlated, that's to say, just stay away from one another on opposite sides of the nucleus, again, because they repel one another. As far as the expansion is concerned of the wave cloud, one of the ways of viewing this is to say that each electron partially screens the charge of the nucleus as seen by the other electron. That is to say, the electron cloud is like a cloud of negative charge, and this interposes negative charge between one given electron and the nucleus, thereby diminishing the charge of the nucleus. So what this suggests is a trial wave function, which is based on a nuclear charge, which is not the true nuclear charge, but rather an effective one. If I write the single particle wave function for the ground state of hydrogen-like atom 100, and I'll write it as semicolon Z sub E, where Z sub E stands for an effective nuclear charge, as a function of position, let's call it R. That's given by ZE cubed over pi to the 1/2 power, which is just the normalization, of course. Then it's e to the minus ZE times the radius R. And this is, of course, in atomic units. Now this is just the standard formula for the ground state of hydrogen or hydrogen-like atom, except I've written ZE, Z effective here instead of the true nuclear charge. So the idea is that we'll construct a trial wave function, I'll call it capital psi. It's a two-particle wave function, which will be a product of these single particle wave functions with an effective nuclear charge. I'll write this as in ket language as 100, 100 Z sub E. The 100, the NLM quantum numbers of the ground state. So this is just two 1s orbitals here with an effective nuclear charge. And then in accordance with and these are normalized. So then in accordance with the variational principle, we need to construct an energy functional. I'll call it the energy to be a function of the effective nuclear charge. And it's just this psi sandwiched around the Hamiltonian. So it's just psi sandwiched around the Hamiltonian H, like so. And then we want to minimize it with respect to the effective nuclear charge. Now the Hamiltonian H, I'm going to write in a certain way. It's going to be kinetic energy of particle 1, electron 1, P1 squared over 2, minus Z effective over R. Take that as one term, plus P2 squared over 2, minus Z effective over R. That's the second term. Then we have a term which is Z minus Z effective, multiplied times 1. Oh, these should be 1 over R1 and 1 over R2. Those are the radii of the two different electrons. And then this is a correction term. It's Z minus Z effective times 1 over R1 plus 1 over R2. And I'm not done yet, but let me explain what I'm doing so far, is that in the first two terms, of course, we have hydrogen-like single particle Hamiltonians here, but with the wrong nuclear charge. It's Z effective instead of the true Z. And what this term does is it compensates. It multiplies, for example, 1 over R1 times the difference, Z minus Z. And if you add that term times 1 over R1 to the minus Z over R1 you find there, it adds up to give you Z over R1, which is the correct term in the actual Hamiltonian for helium. Finally, we have the inner electron potential, which is 1 over R12. So this is the helium Hamiltonian, really no change at all, just written in a certain way. And I'll number.
Sorry to interrupt.
Yeah, go ahead.
Should we have that Z effective and that Z swapped in the second term?
Oh, yeah, you're right. There's a question of sign, isn't there? Yes, I said it wrong. I want to add Z effective and subtract Z. Thank you very much for that. Yes, that's correct. Because it's supposed to enter with a minus sign. And I can see also the little doodads on my screen are getting in the way. All right, so anyway, there's the Hamiltonian. Let me label these terms 1 through 5, 1, 2, 3, 4, and 5 like this. And so to carry out the variational principle, we need to compute the expectation value of the Hamiltonian. So let's write psi here. We have psi here as a bra and a ket, and here's the psi expanded out. Let's write out this more explicitly. So let's talk about the term number 1 first. Let's call it T1 is equal to the first term here. So it's going to be 100, 100 Z effective as a bra. And then we have P1 squared over 2 minus Z effective over R1. That's the operator in the middle. And then we've got the same state as a ket, 100, 100, and Z effective on the right. Now the operator in the middle involves the momenta and coordinates only of electron number 1. But the bras and the kets on the right involve both particles 1 and 2. There's a bra for particle 1, and over here is the ket for particle 1. And down here is the bra for particle 2, and there's the ket for particle 2. Let me label this as the 2, and this is the 1. Now the operator in the middle, depending only on the coordinates of particle 1, doesn't affect the variables for particle 2. So the bra and the ket for particle 2, this operator in the middle is just really transparent to that bra and the ket. And those two combine together by orthonormality just to give you 1. And the result is you end up with a matrix element involving only the coordinates of particle 1. So this is the same thing as just 100, single particle matrix element with effective nuclear charge. The same Hamiltonian, I'll write it as P squared over 2 minus Z over R, Z effective over R. And then on the right-hand side, I got 100 semicolon Z effective. And I didn't put 1 subscripts on this anymore because particle 1 is the only particle that's left anymore. So I'm just called variables in question. Let's just call them P and R without any subscripts. You might as well do that. All right. So this is now a single particle matrix element. And in fact, it's the expectation value of an effective Hamiltonian, hydrogen-like Hamiltonian, with respect to one of its own eigenstates. So therefore, the expectation value is just the eigenvalue. And that's the same thing as minus ZE squared over 2, using hydrogen as basically a hydrogen formula for a hydrogen-like atom. And this is the same thing as so this is T1, and this is the same thing as term T2, because in T2, we just have particle electron 2 instead of electron 1. So by swapping labels 1 and 2, it's the same analysis, and you get the same answer. So this takes care of the first two terms of the Hamiltonian. Now, as far as the third term, we want an expectation value of 1 over R1. Let's look at that one. So I have two particle Bronsted-Ketz, 1, 0, 0, 1, 0, 0. And then let's take 1 over R1 here, like this. And then 1, 0, 0, 1, 0, 0, semicolon Z effective, like so. This is part of, I'm omitting for ZE minus Z factor here. I'll bring that back in a minute. Let's just look at the 1 over R1 up here. That's the operator in the middle. So now it's the same story. This is an operator that depends only on the coordinates of particle 1. And so we can effectively just annihilate or just cancel out by orthonormality the Bra and the Ket for particle 2. And this just turns into a single particle matrix element of 1 over R, 1 of the radius 1 over R. Well, these are one of those expectation values we did last semester. And in fact, this just becomes equal to ZE divided by the principal quantum number N, which is just ZE now because N is equal to 1 here because this is the ground state. And therefore this gives us the expectation value of 1 over R1. And so to write T3, the third term then, that's going to be this prefactor ZE minus Z multiplied times ZE. All right. And then term 4 is going to be the same because it just swap labels 1 and 2 and go through the same analysis. So T3 is equal to T4. Okay. Now then, let's do T5. That's the last one, 1 over R1, 2. Let's see if I got room for it here. So in the case of 1 over R1, 2, I probably have room to put it on this page. Let me do that. So what we've got is 1, 0, 0, 1, 0, 0, Z effective, sandwiched around 1 over R1, 2. Okay, that's what we need. Now 1 over R1, 2 is a 2-particle operator, depends on the coordinates of both the particles, obviously. So this is going to turn into a 6-dimensional integral. It looks like it's going to be trouble. Actually, it's not based on what we've done so far, because this is exactly the same matrix element that we evaluated in doing first-order perturbation theory on the ground state of helium. The only difference is instead of a Z effective there, we had the true nuclear charge. But the calculation goes through in just the same way as before, just with Z replaced by ZE. And perhaps you remember the answer, it was 5/8 Z, so now this becomes 5/8 of Z sub E, like so. And so really, having done the perturbation theory, working out these matrix elements for that are needed for the variational principle are not so hard. So if we add them up, we get an energy functional. Let me call it E as a functional of Z effective, E of Z effective. What is it? It's twice T1, so it's twice minus Z squared over 2. So that's minus Z squared, ZE squared really, Z effective squared. Then we added that twice T3. So we add plus 2, the quantity Z effective minus Z times Z effective. And then we add finally the 5th term, which is 5/8 Z effective. And if you simplify this a little bit, it turns into Z effective squared minus twice Z effective times Z, and then plus 5/8 of Z effective. All right. And then following the principle, the principle of the variational principle, we want to compute the derivative, dE dZe. We want to minimize this function, so we compute the derivative. And you can see it's twice ZE minus twice Z plus 5/8. And we set that equal to 0, and we solve for ZE, and you can see that ZE is equal to Z minus 5/16. Let me box that because that's the effective nuclear charge. So this is the effective nuclear charge, which minimizes the energy. Now, one electron it's physically logical that one electron can only screen, one unit of charge from the other electron. In fact, it's likely to do less than one. So what we would have expected from that line of thinking is that the effective nuclear charge ought to lie between Z minus 1 and Z. This is just a way of saying we can't screen more than one unit of charge with one electron. And indeed, this is what's happened. We find the screening is 5/16 of a nuclear charge. Now, in order to get the minimum energy, which is the estimate of the ground state energy, we need to take this E of ZE and plug this in, using this form. Here's the formula. We need to plug it in up here. You see right there, and the ZE has to go in there. Plug this in. And if you do expressing it in terms of Z, and if you do the algebra for this, I'll skip the details, but it's straightforward to do it. Just rearrange this quadratic. What you find is that it's minus capital Z squared plus 5/8 Z minus 25 over 256, would you believe? So let me box that, because this is now the estimate of the ground state energy based on the variational principle. And it's kind of an interesting result, because the first two terms are what we got from first order perturbation theory. This is what I called E first order of the ground state. The first order estimate in perturbation theory, the ground state energy was minus Z squared plus 5/8 Z. And the variational, and that was already, we already pointed out, that was already variational. That is to say, it was an upper bound to the true ground state. But now we've got a different with a different trial wave function, we've got a different variational estimate, and it's less. So this means that this new one is going to be closer to the ground state energy by an amount which is roughly about 1/10 of an atomic unit. So that's you see, the variational principles actually work better than perturbation theory here. All right. So let's put this in let's look at the numbers. Let's put this in a table and see what it does for us. And I've assembled the table here for you, so I don't have to write it all out. Here it is. The two interesting cases are the H minus ion and the helium atom. Let's do helium first. The true charge is 2, of course. The effective charge is 5/16 down, so that's 1 11/16. The results of perturbation theory are given in the next two columns. Here's the ground state in the unperturbed system. Here's the result after the first correction due to perturbation theory. That's adding the 5/8 Z up here in this formula. The variational estimate involves subtracting from that 25 over 256, and this brings the minus 2.75 down to minus 2.848. You do the numbers. Whereas the exact ground state energy is minus 2.904. So if we put this on a chart to see how it's going here, what it did, here is the diagram I showed you the other night. -4 is the unperturbed energy. First order perturbation theory raised it up to minus 2.75, which was too far. And what this variational correction is doing is it's closing about 2/3 of the downwards of the difference which is left. So the variational method, you see, is doing better. It's closer to the true ground state. In fact, it's not bad. Look at on this diagram here. It's actually not bad considering we just had a trial wave function with a single parameter.
Is it better than going to second order in perturbation theory?
I don't know, because I've never tried to do the second order. Second order perturbation theory is in many cases is difficult to do because it involves a sum over an infinite number of states. It began actually as a resolution of the identity. If you remember what the formula looks like, there's that sum in there. And sometimes the sum can be done analytically, but otherwise it's hard to get a handle on. You can do it numerically, perhaps, So the answer is I really don't know. I don't know what the second order would do. By the way, the second order second order perturbation theory is not variational. So even if we calculated, we wouldn't even know whether it was too high or too low. In that sense, this is better. To get really good estimates of ground state energy, perturbation theory is kind of a losing proposition because each higher order term involves more and more multiple sums. Whereas the variational method just involves more complicated trial wave functions, which is usually easier to do in practice. I'll say something about that in a minute. In any case, that's the story with helium on this analysis. If we look at H minus, Here's the results. We have 11/16 of the charge is seen, according to this variational estimate. The next two columns again are the results of perturbation theory. We were disappointed because the results of first order perturbation theory gave us an energy which was above the continuum threshold, and therefore did not provide us with a theoretical proof of the existence of a bound state of the H- ion. Well, here's the variational result. It's minus 0.473. It's better than it was, but it's still, unfortunately, is not below minus 0.5. So even with this variational estimate, we still don't have a proof that H- exists. And if we didn't know it experimentally, we'd still be up in the air. So it'd be a research project to do it. Here's the true ground state energy. As you see, it's slightly below minus 0.5. In the case of H-, the reason that our variational calculation didn't give us a bound state, didn't give us a proof of a bound state, is because it doesn't have enough physics in it. All we did was we varied the Z effective, but we had otherwise two hydrogen-like orbitals sitting on top of one another. And this does not take into account the tendency of the two electrons to stay on opposite sides of the nucleus. So what we need is a more complicated trial wave function in which that's really a correlation between the two electrons, in which that correlation is taken into account. If you do that, you can get variational estimates that are below minus 0.5, and thereby give you a theoretical proof of the existence. So that's some interesting issues that arise in this ground state perturbation of helium. These types of variational calculations of helium, especially for the ground state, were first carried out in a serious way by a guy named Hilarius going back to the 1920s. He must have spent years doing this because he was working entirely by hand. There wasn't even any desk calculators, not much in those days. And he kept working on more and more sophisticated trial wave functions, and eventually got estimates for the ground state energy of helium that were quite good. Nowadays with computers, of course, it's possible to go to very high accuracy. In fact, one knows these numbers. One knows the ground state energy of this. Well, I have to say that this Hamiltonian we're working with is not the physical Hamiltonian for real helium, because we neglected a number of small effects. We neglected the mass polarization terms having to do with the finite nuclear mass, and we neglected fine structure as well as the Lamb shift and other things as well. So one can distinguish the true ground state of helium versus the ground state of this electrostatic approximation to it. In any case, the ground state of the electrostatic approximation is known to nowadays, I don't know how many it is it 15, 16 significant digits? It's only limited by how much computer power you want to throw at it. In any case, it's way, way beyond the accuracy needed to see the difference between the electrostatic Hamiltonian and these other corrections like fine structure and so on. Those, of course, can be computed as well and included in the mix. At a certain point in history, there was interest in this in order just to simply test quantum mechanics. I mean, if you wonder whether quantum mechanics is a correct theory, this is one of the ways you do it, is you put it in high precision tests of real problems. And this has certainly been done with helium. Okay, so that is an outline of an interesting example of a non-solvable problem using both perturbation theory and variational method. Are there any questions about that before I move on to another? This is really all I want to say about helium. Are there any questions before I move on to another topic? All right. If not, then I'll tell you what the next topic is, and we'll get started on it. The next topic is multi-electron atoms. So let's talk about them. This is now generalizing to not just Z equals 2, but rather to any Z. This will be our first excursion into what's usually called many body theory, and we'll develop a somewhat simplistic version of a set of techniques for dealing with many body theory, but they're the basis of more sophisticated stuff that we'll pick up later in the course. So let's talk about an N electron atom. It has N electrons. The number of electrons doesn't have to be the same as the nuclear charge. So let's let Z be the nuclear charge as usual. If N is less than Z, you have a positive ion. If N is greater than Z, you have a negative ion. We know that such ions do exist. You know, their chemistry is full of them, you know, it's the calcium plus ion and so on. So they certainly exist. And by allowing these two things to be different, we incorporate the ions as well as neutral atoms. Neutral atoms would be a case where Z is equal to N. Let's start with an electrostatic model for the system. It's numerically quite good, and if Z is not too large, it's good, and it's a good starting point. So the Hamiltonian then looks like this. It's the sum on I equals 1 up to N, the number of electrons of the kinetic energy, which is pi squared over 2, minus Z over Ri, which is the potential energy of interaction with the nucleus. And then there's the sum of I less than J of 1 over Rij, which as the notation I think is clear, that's the distance between electron I and electron J. And let's call these two terms H1 plus H2. Now, the H2 is not really small compared to H1. Although it doesn't have a factor of Z in it, because it's a sum over pairs of electrons, it's proportional to Z to N squared. You see, there's a lot of terms in there. It's a number of pairs, and so it's actually quite comparable to H1, and it's not profitable in a multi-electron atom to treat H2 as a perturbation. We did that with helium, but that was marginal anyway. It gave us some quantitative, but mostly semi-quantitative results. All right. Anyway, we're not going to use perturbation theory in this. We're going to use the variational method. And the 1 and 2 subscripts here then have the following significance: is that H1 is a sum of terms of operators where each operator refers to the coordinates, the position, and the momenta of just one electron at a time. In other words, a sum of 1 electron operators. Whereas H2 is a sum of 2 electron operators. Each term depends on the coordinates of only 2 electrons at a time. In Coulomb problems, electrostatic approximations, these are all you have. You don't have any 3 electron operators and so on. Not with this approximation. So this is actually quite common in practice. In other systems, we do have multi-particle operators. In any case, this is a breakdown of the electrostatic Hamiltonian for multi-electron atom. Now then, before we embark on any serious calculations, let's look at symmetries that this Hamiltonian possesses. One of them is given by angular momenta. The total orbital angular momentum of the system is just the sum of the electrons, I equals 1 to N, of the individual orbital angular momenta L sub I, like this. The term H1 actually commutes with the individual orbital angular momenta. If I have, L1 and the term, I equals 1 up here, they commute because it's a central force Hamiltonian. And if the I here and the I up there are not the same, if it's an I and a J, they commute because they refer to different degrees of freedom. So each of these terms here commutes with each of these LIs. And so there's a lot of symmetry there. It commutes with the orbital rotations of individual electrons. However, the inner electron potentials don't commute with individual electron rotations. If I have the distance between particles 1 and 2 and I rotate particle 1 but not particle 2, it's just obvious that changes the distance. So as far as the whole Hamiltonian is concerned, it's only the total L and not the individual L's, which is a good quantum number. It's really a collection of good quantum numbers. It's a vector. The operators that commute with the Hamiltonian. The components of L commute with the Hamiltonian, but they don't commute with each other. If we want operators that do commute with each other as well as the Hamiltonian, we can form functions of L, which the usual choice is of course L squared and LZ. So let's suppose we do that. Now we have 3 operators that commute. This Hamiltonian doesn't depend on the spin at all, so it commutes with all spin operators. Useful spin operators to think about are the total spin, which is just the sum of the spins of the individual electrons, like this. Total spin is a useful operator to consider because it commutes with all permutations. and therefore is a physical operator. I'll say more about the requirements, symmetrization requirements in a little bit, but it's symmetric under permutations because you just rearrange the terms and S goes into itself. And only such operators can be physical. So the S total is a physical operator. And again, to create operators that commute not only with a Hamiltonian, but also with each other, will reduce S vector into two operators, which is S squared and S sub Z. So we can start to make a table of operators that commute with a Hamiltonian. There's L squared, LZ, S squared, and S sub Z. And there's also parity, I'll include that. And so if these are the operators, then we can write the quantum numbers. Am I running off the screen yet? No, it's still visible here. I'll move it up some. Let's call the quantum numbers, let's call it capital L, capital M sub L, capital S, capital M sub S, and just pi for parity. Using capital letters here to indicate the quantum numbers for the whole atom. Again, this is a convention that I mentioned before. I'll use this in talking about multi-electron atoms. Capital letters refer to the quantum numbers of the entire atom, but I'll use lowercase letters to refer to the quantum numbers of single electrons. All right, anyway, these are all quantum numbers of the whole atom. In addition to that, the Hamiltonian commutes with exchange operators. In helium, there's only one exchange operator exchanging the two electrons, but now there's a whole collection of them. There's an exchange operator for any pair of electrons, I and J, so it's EIJ. Hamiltonian commutes with all of them. However, these don't commute with each other. And the study of the exchange operator leads us into the more general concept of permutations, and I'll develop that topic hopefully in a few minutes in this lecture tonight. This collection of operators here that commute with the Hamiltonian is really basically the same one that we had in helium. There's nothing new here. It's slightly generalized to account for multiple particles. But what this means is that ultimately the eigenstates of the atom can be organized as eigenstates not only of the Hamiltonian, but also of L squared, LZ, S squared, and S sub Z, and also of parity. And there's going to be issues involving symmetrization as well. And we'll see as we progress how that works out. So that's something to keep in mind about where we're going. Now, the method that I'm going to use for attacking the multi-electron atom initially is a method that's due to Hartree. Hartree's method is variational. It's based on a certain trial wave function. It has some serious defects, but it's also somewhat simpler than more complicated theories that don't have those defects. So we'll start with the Hartree's theory first. Going through it, we learn some things by going through it that'll help us for what we want to do later. So being a variational method, Hartree has a trial wave function. And what does it look like? I'm going to call it capital phi. I'll use capital letters for wave functions of the whole atom. And I'll put an H subscript on it where the H stands for Hartree. So this is Hartree's trial wave function. And Hartree basically says, let's construct a multi-particle wave function, which is a product of single particle orbitals, one for each electron. I'll write it this way in Ket language: orbital 1, particle 1, orbital 2 for particle 2, ... out to orbital n for particle n. Now the word orbital here it has a meaning. An orbital is a single particle wave function. And that's the definition of it that we'll use here. It may or may not include the spin. It depends on what we want to do, but it's always a single particle wave function. So this 1 and 2 here and n here and so on, these are the orbitals. Whereas the parenthesized numbers here, we'll let those stand for the electrons. And so the idea of Hartree's trial wave function is that we have made an assignment of certain single particle orbitals to the electrons in some order, and we just multiplied them together to create an n particle state, which is Hartree's state. Now, I want to use a convention here is for I'll use indices I, J, etc., which go from 1 up to n to stand for electrons. And I'll use Greek indices lambda, mu, and so on, which also go from 1 up to n to stand for orbitals. it's convenient to do this to keep these two types of objects distinct while we go through the theory. Otherwise, I think you can get confused pretty easily. I think Cummins' book is a little bit confusing on this issue. In any case, let's adopt this convention. Now, if I take one of these orbitals, let me call it lambda, it's one of the list up here, one of these orbitals. We will make an assumption about what it looks like. We'll assume it's a product of a spatial part, I'll call U sub lambda, multiplied by a spin part, I'll call M sub S sub lambda, where M sub S sub lambda is a magnetic quantum number, which is equal to plus or minus a half. And what we're going to do is just simply assign either spin up or spin down, in other words, the value of M sub S lambda to each one of these orbitals before we when setting up the Hartree trial wave function. It's just be a part of the setup of the wave function. We'll just assume that some are up and some are down. There's actually no loss of generality in that, because the Hamiltonian we're trying to solve is a purely orbital operator and doesn't involve the spin. And so it actually possesses eigenstates that are also eigenstates of the spin up and spin down of each individual electron. So by making these assumptions, we're not losing any generality by doing that. As far as the spatial part of the wave function is concerned, this is going to correspond to a spatial wave function, I'll write as U lambda of R, which is otherwise the scalar product of the R ket with U lambda in ket language, like so. And Hartree's idea is that it is the spatial parts of the wave functions which are the variational parameters. Now, in the case of the calculation we just did for helium, the variational parameter was a single number. It was the effective nuclear charge, just one number. So we had a one parameter family of trial wave functions. In this family of trial wave functions, the parameters are actually the single particle orbit, spatial parts of the single particle orbitals. That is to say, it's the entire function. Moreover, there's not just one of them, but there's n of them because there's n orbitals. So what we want to do is to find the single particle wave functions as functions in three-dimensional, complex functions in three-dimensional space, which are going to minimize the energy with respect to this orbital. That's the plan. It's Hartree's idea. Okay. So each of these wave functions is in effect, it has an infinite number of parameters because it's a function and has a different value at each point of configuration space. So those values are the variational parameters. There's an infinite, continuous infinity of them for each one of the U's. All right. Now let's see. Yeah. So when we use the variational method, you can write down any wave function you want as a trial wave function. The world is yours to do that. However, you can't expect to get good answers unless you have some reason for why it's something that's close to the true ground state or represents the actual ground state wave function. Sometimes that's mathematical and sometimes it's physical. So in the case of Hartree's wave, the logic is, so in the case of Hartree's wave function, the question is, what is the reasoning that makes us write this down, that makes us believe this might be a good approximation to the ground state? And the reasoning runs something like this, is if I have my multi-electron atom here with the nucleus at the center, then there's an electron cloud. Of course, electrons are all orbiting around somehow inside this electron cloud, inside the atom like this. And if I pick one of these electrons, E minus, and you think of it classically as moving on an orbit like so, what one can imagine is that the effect of the other electrons on this given electron is produced by the electron cloud of the wave functions of the other electrons. The wave function implies a distribution of probability in space, and that corresponds somehow to a cloud of charge. So we can imagine a picture, at least, I hesitate to call it an approximation, but a picture of the atom, which is clearly only an approximate picture, because it's not exact, but it's an approximate picture, in which we visualize each electron as moving in the average field produced by not only the nucleus, which is a fixed field, but the average field of all the other electrons. And so if we do this, then it's as if each electron moves in, it has a Hamiltonian, which involves, first of all, a kinetic energy as usual, an energy of interaction with the nucleus, which of course has to be there, but then plus an average potential energy, which, as I say, depends on the electron clouds of the other electrons, like this. Moreover, there's nothing that says it has to be a central force potential, so maybe it depends on R vector instead of R scalar, like this. And then the problem would be to determine this V average, which is due to the clouds of the other electrons. But if we could do this, then each electron is moving now in a single particle Hamiltonian like this. So in effect, the original Hamiltonian, if we do this, then the original Hamiltonian, where is it here? Have I? Yes. Here's the original Hamiltonian. We broke it up in H1 and H2 terms. Remember, this is one particle and two particle terms of the full Hamiltonian. Effectively, we're going to replace this by another Hamiltonian, which is the sum I equals 1 to n of pi squared over 2 minus z over ri plus v average of ri. In other words, now it becomes a sum of single particle terms. The two particle terms have been replaced by single particle terms. All right. So there's some kind of approximation that does that. Now, what's interesting is that if this really were the Hamiltonian for the system, it now becomes a sum of operators, single particle Hamiltonians that depend on the coordinates and momenta of only one electron at a time. And therefore, the multi-particle Schrodinger equation is separable. And the final wave function then is a product of single particle orbitals, each one of which is an eigenfunction of these separate Hamiltonians. And if that's the case, it gives you a wave function that looks just like Hartree's trial wave function, in which the orbitals 1 through n and so on are the single particle eigenfunctions of this Hamiltonian here. Let me call it lowercase h. They're eigenfunctions of this single particle Hamiltonian there. So this is in effect, the physical reasoning behind Hartree's trial wave function. Now, not as all perfect with the world, however, there are some problems with this. One of the problems is that if we imagine an electron as being influenced by the other electrons by means of their average electron clouds, then what we see is that each electron is influenced by all of the other electrons, but not by itself. And what that means is that we need to exclude the electron cloud of the given electron from the charge cloud, which is influencing that electron. In other words, we don't want to count self interactions. There are no self interactions here. But what that would mean is that each individual electron sees a different average cloud. We can fix that up just by putting an I subscript here on the V average, like this on this Hamiltonian, like so, meaning that the ith electron has its own potential. If we do this, the Hamiltonian is still separable, and the solution is still a product of single particle orbitals, as in Hartree's theory, but the orbitals themselves are no longer eigenfunctions of a single particle Hamiltonian, but rather each one is an eigenfunction of a different single particle Hamiltonian. That, of course, means that they're no longer orthogonal to one another as they would be if they belonged to the same Hamiltonian. Okay, so that's one issue, is that the electrons don't act on themselves. The second issue, which is a bigger one, is the fact that Hartree's trial wave function is not properly anti-symmetrized. It doesn't satisfy the requirements of the symmetrization postulate. It's easy to see. It doesn't change sign under the exchange of two electrons. We'll fix that up later. What we'll do for now is just ignore that and proceed with it using the variational principle. All right. So this is some of the logic behind the Hartree wave functions. Now, in the Hartree trial wave function, let me write it out again. The Hartree trial wave function phi Hartree is orbital 1 for particle 1, orbital 2 for particle 2, and so on, like this. Orbital capital N for a particle capital N. We will have to assume that these single particle orbitals are normalized, that lambda mu scalar product is equal to Kronecker delta mu nu. I'm sorry. I'm sorry. I'm saying this wrong. I'm sorry. I'm saying this wrong. I said it right. I wrote it wrong. We want to assume that these are normalized. The single particle orbitals at lambda scalar product with lambda is equal to 1. We need to do that because if we don't normalize the wave function, then you don't get a minimum. I mean, you just let the wave function go to 0, for example. You need to normalize them. So we'll assume that this is true. We'll later on have to enforce this condition by Lagrange multipliers. By the way, this implies, since the spin parts are the same of these two orbitals, this just implies the orthonormality of, the normalization of the spatial parts of the wave function. U lambda is equal to 1. Of course, that's the same thing as, I'll call this a normalization integral in lambda here is the integral d cubed. I'll tell you what I'm going to do. I'm going to write it in a separate piece of paper. Normalization integral in lambda is the integral d cubed r of u lambda of r. Remember, the u lambda of r are the variational parameters. This is a constraint which we're going to have to impose later on. So this in lambda, which is equal to this integral d cubed r, et cetera, is equal to 1. All right. All right. So now to proceed with Hartree's theory, then we need to compute the expectation value of the Hamiltonian. We want to sandwich Hartree's trial wave function around the sum of the two major terms from the Hamiltonian, the 1 and 2 particle operators. Let's do the H1 first. For the H1 term, it's going to look like this. It's going to be the sum lambda equals 1 to n. Phi Hartree as a bra is bra 1 for particle 1, bra 2 for particle 2, out to n for particle n. The operator in the middle is pi squared over 2 minus z over ri. And then we have ket 1 for particle 1, ket 2 for particle 2, out to ket n for particle n. And I'm probably running into the doodads on the screen again. Okay, there we go. Let's get that so you can see that. All right, that's the H1 term. To understand this matrix element, let's take an example. Let's suppose that let's do an example, e.g. Let's take the example that I is equal to 2 here. This, of course, is the operator giving us the kinetic energy and the potential energy of interaction with the nucleus. Let's take the case I equals 2. If we do this, then the bra 1 for particle 1 here and the ket for particle 1 over there, just this operator is just transparent to that bra and the ket, and they just combine together to give you 1 by the normalization, which we're going to impose by Lagrange multipliers. And the same thing applies to all the orbitals except for the one for I equals 2. So it applies for 3, 4, 5 all the way up to n. The n, they all go away, and they all just go away by normalization, leaving behind a single particle matrix element, which for the case I equals 2 is going to be this. It'll be orbital 2 for particle 2, sandwiched around what I'll call H2, this operator here for I equals 2, and then orbital 2 for particle 2 is a ket, like so. That's what it turns into. And likewise, similarly for other values of I. And the result is this H1 term now looks like this. It becomes equal to a sum, I equals 1 up to n, of orbital I for particle I, the operator pi squared over 2 minus z over ri, and then orbital I for particle I now is a ket. All right. And this is nice because it's reduced this multi-particle matrix element into a sum of single particle matrix elements. However, this violates our rule of using these Latin indices I and j for electrons and Greek indices for orbitals. So let me write it in a different way as sum from lambda equals 1 to n of orbital lambda for particle I, operator pi squared over 2 minus z over ri, and then orbital lambda for particle I over here, where we'll introduce the understanding that I is equal to lambda. If I take this matrix element and write it out explicitly as an integral, it looks like this. It's the integral. Well, in the first place, the orbital lambda and bra and the ket have a spin part. but the operator in the middle is a purely spatial operator. So the two spin parts are the same on both sides, and they just combine by orthonormality to give you one. So this matrix element turns into a purely spatial matrix element, which I'm not going to write that down here as an integral. It's an integral over position R. We have U lambda of R complex conjugate coming from this bra here. We have this is R sub I here. Then we have pi squared over 2 minus z over Ri as the operator in the middle. And then we have the wave function U lambda of Ri on the right. Okay, that's just what it is. And you will see from the form of this integral that the Ri and the pi, the I subscript, is really just a label of a dummy variable of integration. So we could just drop it. I'll just cross it out here like this, like so, cross it out. It just goes with the I part of this just goes away. And what's left over is something that just depends on lambda. I'm going to define this to be an integral called I sub lambda. And let me go over to my other page here where I'm accumulating a table of integrals. So I sub lambda then is equal to this. It's the integral t cubed r of U lambda of R complex conjugated times p squared over 2 minus z over R times U lambda of R. And you can see what physically what I lambda is. It's the energy of for orbital lambda. It's the energy of interaction of that electron or with that orbital, the sum of its kinetic energy and its interaction with the nucleus. All right. And
yeah,
yes.
can I see the other page actually? I'm a little confused about the I's and the lambdas.
Yeah. So what we did here is we said, let's just look at an example of I equals 2. And if you do that, that means all the bras and the kets go away except for the 2's on the two sides. So you get this for everything was just equal to 2. If
right.
I do this for the other values of I here, this should have been I sum from 1 to n.
Right, okay.
If I do this for the other values of I, then I get the sum like this on all the values of I. But this is breaking our rules about use of indices. So I'll write a lambda here for the orbitals and I'll understand that I is equal to lambda. And then it now looks like this. Now I take this matrix element and write it out as an integral. And when you do that, you realize that the I indices are just dummy variables. And so they just actually just go away. You never needed them anyway. What this integral depends on is the orbital label and nothing else. And so that leads to the integral I lambda, which is this here.
Okay, I see.
Okay, all right, good.
Yeah, thank you.
Now, that's the logic of this. Now, so what that means then is, let me save this page here. Let me get a different pad because it would be easier to swap them in and out if I do. Let's go on to, let's go on here, put this over here. So now let's, this now allows us to write down the value of Hartree's trial wave function sandwiched around our H1 operator. And this becomes the sum from lambda equals 1 to n of I lambda. And physically, as I just mentioned, this is just the sum over all the electrons of the kinetic energy plus the energy of interaction with the nucleus. Now we need to worry about H2. So we want phi Hartree sandwiched around H2, which is the 2 electron operator. And so this is the sum on I for I less than j sum over pairs. Orbital 1, particle 1, all the way out to orbital n for particle n. These are all as bras. 1 over r ij, and then orbital 1 for particle 1, all the way out to orbital n for particle n as kets. All right. Again, let's take an example. Let's take I equals 1 and j, no, let's take I equals 2 and j equals 3. Let's do that one. So this becomes 1 over R23 if we do that. And then you can see that the bra and the ket for particle 1 they don't cancel, they convert in, they combine together by orthogonality to give you 1 is what they do. It's not orthogonality, it's by normalization. We have said that we're going to demand these single particle orbitals be normalized. The question about the orthogonality comes later, but they're normalized. And so 1 scalar product of 1 just gives us 1. And likewise, 4, 5, 6, all the way out to n also give us just 1. And so the result in this example is that we get orbital 2 for particle 2 times orbital 3 for particle 3, 1 over R23 times orbital 2 for particle 2 now as kets times orbital 3 for particle 3 as kets. Okay? And so you can see that this sum turns into the sum on I less than j of orbital I for particle I, orbital j for particle j, 1 over Rij, orbital I for particle I now as kets times orbital j for particle j. Okay? It becomes the sum of 2 particle matrix elements, which is an improvement because previously it was an n particle matrix element. All right. Now again, we're violating our rules. So let's write this in another way. Let's write as the sum on lambda less than mu, orbital lambda for particle I, orbital mu for particle j, 1 over Rij, orbital lambda for particle I now as kets, orbital mu for particle j as kets, like so. And if we take this and write this out explicitly as an integral over the coordinates of particles I and j, what you'll find is that those are just dummy indices. And the net result is that this thing can be written in the following way: as the sum on lambda less than mu of certain integrals, which I'll call j lambda mu. And basically what they are is orbital lambda, orbital mu. It's a 6-dimensional integral because it involves 2 orbitals. The orbital lambda and orbital mu multiplied together divided by the Coulomb denominator. So this j lambda mu integral that comes out, I'll put it over here on our summary page, turns into this. It's, instead of calling it Ri and Rj, I'm just going to call it R and R prime. They're just dummy variables of integration, d cubed R prime. Then we have u lambda of R, absolute value squared, times u sub mu of R prime, absolute value squared, divided by the Coulomb denominator R minus R prime. That's what we get for the Hartree's expectation value of the 2-particle operator. It turns into this. So it's a sum of pairs of these integrals j lambda mu. Well, we had a simple interpretation, physical interpretation of the I lambda. What's the interpretation of the j's? It is the following. We actually saw it before in helium. The j lambda mu's are actually direct integrals of the same type that we saw in the perturbation analysis of helium. That's to say, u lambda squared is the probability density in 3-dimensional space corresponding to orbital lambda. Same for u mu. And what this integral represents, interpreted in electrostatics, is that it is the energy required, electrostatic energy required to bring the 2 charge clouds, initially at an infinite separation from one another, into their final location. That's what this integral means. So it's called the mutual electrostatic energy of the two electron clouds. So what we're finding here is that there's a contribution to the energy of the Hartree functional, which is the sum over pairs of those electron clouds. Notice that it's only lambda less than mu, which means we're just summing over pairs of distinct electron clouds. So that's what you want. This is an energy, in fact, that you'd expect to see in this problem. Except before, when we did it, it wasn't variational. It was part of a perturbation calculation that gave us a shift in an energy. Whereas here, as part of a variational calculus, part of the energy functional, we're going to ultimately try to minimize. Okay. Now, to go back to these direct integrals, they have certain properties. One of them is it's obvious that they're positive because the integrand is strictly positive. Besides, the clouds are electrons, so they repel each other. So to bring them together, it takes a positive energy. They're also symmetric in the 2 indices, mu and lambda and mu. If you swap the 2 indices, it's easy to see. If I swap lambda and mu, and then I swap the dummy variables R and R prime, this integral goes into itself. So they're real and symmetric entries here. By the way, the contribution to the energy functional only involves pairs of distinct orbitals. we don't summon lambda equals mu, but you might wonder what the value of J is if we set lambda equals to mu. And the answer is that if you do that, what you get is twice the, so what's it called in electrostatics? You get twice the, not the mutual, but the self energy, the self electrostatic energy of the electron cloud. In electrostatics, one normally defines the self energy of assembly of charges as the energy needed to bring the charges in one at a time from infinity. If it's a continuous distribution of charge, you imagine dividing it up into infinitesimal charge elements and then bringing them in one at a time from infinity to assemble the charge cloud. If we do this for one of these, if lambda is equal to mu, if we do this, one of these lambda equals to mu, the energy required to assemble that cloud is 1/2 of J lambda lambda. It's a half because you bring them in piece at a time. So this is just standard electrostatics. But those terms don't appear here. And as we'll see, the reason is because each electron does not act on itself. It's only acted on by the other electrons. That's going to come out of this. All right. Anyway, this sum here with lambda less than mu is conveniently represented as 1/2 the sum on all lambda and mu which are not equal to one another, say omitting the diagonal terms, because that turns out to be more convenient in the analysis. All right. So now what this means is that we can now set up a functional, and the functional depends on the collection of the spatial wave functions u lambda of r. I'll write it like this. And it's equal to, for the single particle terms, is some lambda equals 1 to n, let me draw a line here, of I lambda. And then we have a term which is plus 1/2, the sum on lambda not equals to mu, all pairs that are not diagonal, of the J lambda mu. And this then is the energy functional for Hartree's trial wave function. Now we need to introduce Lagrange multipliers to require that the single particle orbitals be normalized. And so I'm going to subtract off another term, which is the sum on lambda equals 1 to n of Lagrange multipliers I'll call epsilon lambda. And then this is multiplied times the normalization integral in lambda minus 1, like so. And you can see if you regard the Lagrange multiplier as a variational parameter, varying that gives you n lambda equals 1. That's the normalization condition. Oops, you can see it if I move it past the obstacles on my screen here. There you go. So this is the Hartree functional. Okay, now we need to get the Hartree, we need to get equations for the unknown orbitals. Those are the things we want. So what we'll do is we'll make a variation in F corresponding to variations in the orbitals. And then we'll demand that this be equal to 0 for all variations in the orbitals. This is equivalent to computing functional derivatives. One would be the variation of F with respect to u lambda of r. Now, the u's are complex functions. So we've been through this before. If you want to minimize something with respect to a complex function, you need to vary with respect to both the real and imaginary parts independently. But that is equivalent to varying u and u star as independent complex variables, which is algebraically simpler. So let's do that. If we vary with respect to u, we're going to get this variation is 0. Varying with respect to u star, it's delta f with respect to u star lambda of r is equal to 0. And I don't know if my one math student is still here with me tonight, but if you are, star is what physicists use for what mathematicians call right as an overbar. It just means complex conjugation. Star means something else in math. Anyway, you can't do quantum mechanics without doing stars. All right, anyway, so these are the two equations. Now, as it turns out, is normal in situations like this, these two equations are complex conjugates of one another. And so we really only need to work with one of them. It's more convenient to work with the one where we vary with respect to u lambda star. So if I take this functional here and I vary with respect to u lambda star, let's see what happens. So first of all, if we look at the I lambda, here's the I lambda integral down here. The u lambda star is right there. So this u lambda is going to go and replaced by delta u lambda star. That's what we'll get. as far as the J integral is concerned, the U lambda star occurs not only in this part here where I have U lambda squared, but also the U mu squared. So there's going to be two terms that emerge. So if I write this out, then I'll vary F, get the variation in F due to variations in U lambda star. So first of all, we get the sum lambda equals 1 to n. This is coming from the I lambda. The I lambda is an integral. It's an integral d cubed r. Then we get delta U lambda star of r. Then we have p squared over 2 minus z over r. Then we have U lambda of r. Then for the J mu nu term, we're going to have plus 1/2. This is the sum on both lambda and mu, but subject to the constraint that lambda is not equal to mu. And then the J mu nu, now the J mu nu, when we vary the starred u's, there's going to be two terms coming from these two squares here. So what we're going to get is an integral d cubed r prime. I'm writing this out in some detail because I'm afraid you'll be confused about calculating functional derivatives if I don't do it this way. So in the first one, we have delta U lambda star of r times U lambda of r times the absolute value of U sub mu of r prime squared divided by Coulomb denominator. And then there's a second term, d cubed r prime, which involves the absolute value of U lambda of r squared times delta U mu star of r prime times U mu of r prime divided by Coulomb denominator. And then finally, from the normalization integral, we just needed to worry about the n. The n is pretty easy. It's just going to U star U here. So the variation on that gives us plus the sum lambda equals 1 to n of epsilon lambda times the integral d cubed r of delta U lambda star of r times U lambda of r. Okay? And we want to demand that this equal to 0 for all choices of delta U lambda star of r. For all lambdas and all values of r. These are the functions that we want to find that minimize the whole thing. Now I went to some painful writing out things explicitly to get these two terms from the J lambda mu terms. There came two because there was a square of U in one place and a square of the U in the other place. However, these two terms are actually equal to one another. As you can see, if you swap, the first place is a symmetric sum on lambda and mu, and it's a symmetric integral in r and r prime. And if you swap both of them, you'll find that this integral turns into that one. So I'm going to take this integral out like this, and at the same time cancel the 1/2, which is okay. Now, demanding this be equal to 0 for all choices of delta U lambda of r means that we can in effect cancel. We can cancel just cross it out, the variation delta U. At the same time, we can cancel out the lambda sum as well as the r integral, which is what the U depends on. And so if we do this, what we get is that this implies is that p squared over 2 minus z over r, multiplying onto U lambda of r, that came from the I terms here. Then the second term is going to be the sum here. Then we cancel the lambda sum. We cancel the r integration, but not the r prime integration. So it's the sum on lambda, excuse me, it's the sum on mu now, such that mu is not equal to lambda, an integral d cubed r prime of what you see here minus the delta U star. I'm going to write it this way as U sub mu of r prime absolute value squared divided by Coulomb denominator, r minus r prime, multiplied times U lambda of r. The U lambda of r is the same as what I've got here, but I've just moved it over to the right-hand side. And then finally, for the Lagrange multiplier term, I'll bring this over to the other side. That becomes equal to, again, I cancel the lambda integral, I cancel the d cubed r, and I cancel this variation. It just becomes epsilon lambda times U lambda of R. Okay, so this is what we get. And perhaps you can see this now, that what we get is really a form of a pseudo Schrodinger equation, in which we have the kinetic energy and potential energy interaction with the nucleus as the first term. The second term, which came from the two electron operators, is more complicated, but it's something multiplying u lambda of R here, which is also over here and also over here. And the thing that we're multiplying it by, let me put it in brackets here. What is it? Well, it involves a sum on mu, so it doesn't depend on mu, except we exclude mu equals lambda. So it actually does depend on lambda, but it doesn't depend on mu. It doesn't depend on R prime either, because we integrate over that. It does depend on R. Let's define it this way. Let's write V sub lambda of R is equal to the sum on mu, where mu is not equal to lambda, of the integral d cubed R prime of u sub mu of R prime squared divided by Coulomb denominator R minus R prime. And if you interpret what this means, this V of lambda, the meaning of it, in electrostatics, the u mu of R prime, is the charge density of orbital mu evaluated at position R prime. We divide this by the Coulomb denominator and integrate over R prime. The result is that this integral is the electrostatic potential seen at field point R, that's where the potential is shown over here, due to electron cloud mu. And we sum over all mu's except for lambda. In other words, all the electron clouds except for the one orbital lambda that we're interested in here. That's why the left-hand side depends on lambda. The summation is excluding the self interaction. And that's what that is. That's just the intuitive idea that lay behind the whole scheme in the first place. This is sometimes called the self-consistent potential. It's self-consistent because it's only determined once the orbitals are known. But with this substitution, what you see is we have now, I call it a pseudo Schrodinger equation. It's p squared over 2 minus z over r plus v lambda of r. This is really r vector now, multiplying the orbital u lambda of r is equal to epsilon lambda times u lambda of r. This is u lambda of r over here. So the u lambda of r is an eigenfunction of a single particle Hamiltonian, which is a kinetic plus potential Hamiltonian, in which the v lambda of r, part of the potential energy here, is physically the potential produced by the electron clouds of all the other electrons. Now, each one of those, these equations here are called the Hartree equations. Now, each one of those other orbitals satisfies its own Hartree equation. It's driven by the kinetic energy, the potential energy interaction of the nucleus, and the potential energy of all the other electron clouds except for itself. So what we really have here is not just one single particle Schrodinger equation. I'm calling them a pseudo Schrodinger equation because it isn't a real one. There's not just one pseudo Schrodinger equation. There's one of them for each one of the orbitals. And moreover, each of the orbitals has its own Hamiltonian because the V depends on lambda. It depends on which orbital you're talking about. This is just the situation I described earlier. So in order to minimize the energy of the Hartree trial wave function, we need to solve these pseudo Schrodinger equations in this self-consistent potentials. There's more than one. And then when we get those orbitals, those eigenfunctions, we multiply them together and then attach spins to them. And I probably have lost this by now, but we multiply them together, and that gives us then the overall the Hartree trial wave function. All right. So that's Hartree's method. It's physically interesting. This is an example of what's called a mean field theory. Mean field theories are universal when you do many body physics. You'll be doing them all the time if you do any such kind of physics. The idea of a mean field theory is that each individual particle, one approximates it this way, each individual particle is in effect driven by the average field of the other particles of the system. This is one of the few ways that we have of realistically treating many particle systems. It's therefore very common in practice. It's used not only in calculations like this of what we call quantum structure, electronic structure, or nuclear structure for that matter. If you're doing protons and neutrons in a nucleus, is the same story. But it's also used in statistical mechanics, in which the average field produced by the other particles is determined not only by their wave functions, but also by the temperature or other density operators, depending on the problem you're trying to solve. So mean field theories are bread and butter of many body physics, and we're seeing one appear here. Now, how do we solve these equations? These equations are actually simple physically if you think about what they mean, but mathematically they're very complicated because they're actually a collection of integral differential equations for the orbitals u lambda. They're all the equations are coupled together. We can't solve for u lambda for some value of lambda unless we know what v lambda is. And we don't know what v lambda is unless we know what all the other orbitals are. So the way in practice this is done is usually by method of iteration. We start with some guess for the orbitals. This could be based on the Thomas Fermi approximation, which I'm not going to lecture on, but there's a set of notes on it. It's a statistical mean field theory that a simple one, which would allow one to make at least wild guesses, not totally wild guesses for the single particle orbitals. Anyway, you make an initial guess. Once you've got those orbitals, then what you do is you compute the potential energy by this formula here. There's actually a collection of them, one for each lambda. Then you plug these in to these pseudo Schrodinger equations, and now they become real Schrodinger equations with real potentials. So you solve them, then there's a collection of them. They're three-dimensional problems, and you solve them to find the wave functions u lambda. Now you've got a new iteration in which you've got new orbitals u lambda. You repeat the process again. You compute potentials, solve Schrodinger equations again, and you keep hoping that this will converge. You keep doing this over and over again until you get convergence, and then you've got your solution. It's a method of convergence to a solution of, these are really nonlinear equations, giving you a solution of nonlinear equations by iteration. If you ever want to appreciate linear equations, try solving some nonlinear equations sometimes. It'll open your mind. Let me tell you. You don't just go around and say, oh, I assume a solution of e to the I kx, which is what everybody does in elementary physics. It can be much more challenging. In any case, here we do it by method of iteration. So this is the basic basis of Hartree's method. The main disadvantage of Hartree's method is that it does not take into account the symmetrization postulate, so that his trial wave function is not actually physical. It doesn't lie in the physical subspace of the Hilbert space. It may give you some possibly workable answers for the energy levels, but it's certainly not satisfactory. And that's going to be the main issue, which has to be corrected. Before I go on, let me pause here and ask if there's any questions of what I've done so far. I was trying to go a little bit lightweight here on the functional derivatives because I'm not sure that you all understand functional derivatives perfectly well. So I phrased it in terms of making a variation in the orbitals and looking at the corresponding variation in F, and then demanding that the answer be vanished for all choices of the orbital variations, and that gave these equations. If you're accustomed to calculating functional derivatives, there's more efficient ways of doing that.
Could you just briefly go over again why we can cancel out the sums?
Yeah, it's because suppose I have not a functional derivative, but just ordinary multivariable calculus. Suppose I've just got a function of let's say a collection of x's, x1 out to xn like this, and I want to minimize this. So what I do is to minimize this, I want to say that f doesn't change to first order if I make first order changes in all of the x's. So let's do that. Let's replace each of the xi's by xi plus delta xi, where delta xi is small. if we do this, then we find delta f is the sum on I of the partial of f with respect to xi times delta xi. Now we want this to equal to 0. We demand for all delta xi. Well, if this is true for all delta xi, you see we get to cancel the sum here, because we could take all the delta xi's equal to 0 except for one of them, in which case the sum would only have one term. And then setting that one delta xi being non-zero, we'd get that corresponding derivative is equal to 0. So
I
as a,
see.
so as a simple rule, to get the condition we want, we cancel the variation and we cancel the sum. And the result is we get partial of f with respect to xi is equal to 0, which of course would be the usual condition for finding a minimum.
Okay, makes sense.
Now the difference
Thank you.
is if the variables that we are varying are not just numbers, but they are functions themselves, then we're going to have not sums here, but rather integrals. It may be a combination of sums and integrals. In fact, we did have that. We had lambda sums and integrals over r and r prime. And so we're going to end up canceling the lambda sums as well as one of the integral upon which the variation depends.
Mhm.
Okay.
Okay.
All right.
Thank you.
So I'm curious about when you were doing the variation with respect to u lambda star, then how come you had to do the whole chain rule thing where like because isn't the other term u mu, not u lambda?
Yeah. So here's the way to think about it. We're not really varying u lambda or u mu star. What we're varying is u lambda 1, u lambda 2, u lambda 3, all the way out to u lambda n. In one of those sums, those things are indexed by mu, and the other one they're indexed by lambda. But it's the u lambda 1 through u lambda n are what are being varied. So it affects both terms. Do you see?
But then those two terms, then I guess those two terms should be not equal then, right?
No, but they are. You look at them, you'll see they're equal. They're equal because the original thing was symmetric in mu and lambda and r prime. And
oh, right. Okay.
you just swap the two. You know, before you go around canceling the sums and the integrals, you've just got the variation. And in that, those sums and integrals are still in there. And in that variation, you'll see it's symmetric under exchange of dummy indices.
Okay.
It's really nothing but a functional derivative of how, you know, if you take d dx of x squared, you know, you get 2x. So there's a 2 there. And this is just a functional derivative version of that where the 2 comes out. That's really all it is. I went to some pain of writing out both terms, you know, explicitly, but that's what it is. All right. So I thought I was going to get further tonight than I did, but this material takes a lot of writing and the topic is actually a little tricky. So I'm out of time, but this is a good place to stop because where we will pick up next time is with the Hartree Fock method, which is one which incorporates the symmetrization postulate. And it is more sophisticated and much closer to what's normally used in practice. So are there any other questions then about what we've done so far before I turn off the recording?
Yeah, are u lambda and u lambda star treated like as independent
Yes.
functions, sort of like complex numbers or not?
They're treated as independent complex variables. And this is a way of avoiding working with the real and imaginary parts of u lambda. I know this is confusing, but because you want to say, well, if I vary u lambda star, isn't that also varying u lambda? The answer is, you know, roughly speaking, the answer is, it's like this. Let's see if I can say it. It's, if I have a complex number, let's call it W and W star, you know, if I know one, I know the other because I can just change the sign on I. But if I write W in terms of its real and imaginary parts as U plus IV and W star is U minus IV, then the fact that I know how to go from W to W star relies on the fact that U and V are real. But if I promote U and V into complex variables, then it's no longer true that W star is the complex conjugate of W. You follow me? So varying with respect to U and V promoted into complex variables is equivalent to varying W and W star promoted into independent complex variables. I don't want to belabor that too much. I think the easiest thing to say is that if you just try a few examples of this, you'll find that varying the real and imaginary parts of a complex variational parameter are equivalent to varying the U and the U star treated as independent variable. Just try some examples and you'll see how it works.
Okay, thanks. But just a quick follow-up. So is F just a function? It's a functional of just U lambda, not U lambda and U lambda star.
It can actually be interpreted either way, and you want to make it a function of U lambda and U lambda star independently to do what I'm doing. But when you're done, once you're done, you're then free to say, oh, the U's I'm interested in are actually the sum of U plus IV, a real and imaginary part.
Okay, thank you.
Okay, I know this is confusing. The alternative to go through it in detail takes way too much time. I'm sorry, but this is it's a useful calculational technique. All right, are there any other questions?
Brief thing, your screen was frozen for a while. Could you just move the pen so we could see what you've written in the bottom?
I'm sorry if my screen gets frozen. I see it's still frozen because I've moved it and it's not changing at all.
Oh.
And I don't know what to say about that. I'm using an internet connection which has, you're hearing my voice all right, aren't you?
Yeah, your voice is fine.
So was there, look how long it's lasting. Was there freezing screen problems while I was carrying out the lecture?
During the lecture, it was fine.
All right, so I don't know what's happening here. I don't know. Oh, let's see. Did I stop screen share? It's probably because I stopped screen share. That's why. Okay, sorry. All right, so that's not a problem. However, I am getting fiber optics internet installed in my house on February 22nd. So I'm hoping all those problems will go away at that point. All right, any other questions then? All right, then, oh, I didn't stop screen share. I just stopped recording. I don't know what's going on. All right, anyway, now it's time to stop screen share. And then here's stopping recording.